topic for today is 80386 input output architecture. An input output or IO port can be an input port or an output port or a bidirectional port. The input output architecture is the programmer's model of how these ports are accessed. The discussion of this model includes methods of addressing IO ports, instructions which perform IO operations, and the IO protection mechanism. In today's video, we are going to have discussion about this model. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to our channel, kindly subscribe and press the bell icon so that you get notifications for our future videos. The topic for today is 80386 input output architecture. Let us start with the introduction. Say input and output. These are accomplished through IO ports. So IO ports are nothing but registers which are connected to the peripheral device. So when you want to communicate with the peripheral device, you have to make use of the IO ports. Now an IO port can be an input port, output port, or a bidirectional port. So we'll have to configure the port and then use it for input or output. The input output architecture, actually it is the programmer's model how we are accessing these ports. Now here today we are going to discuss the different methods of addressing the IO ports, then instructions which perform the IO operations, and the IO protection mechanism in brief. Let us start with the IO addressing. Now 80386DX microprocessor, it allows IO ports to be addressed in two ways: separate IO address space and memory mapped IO. So in separate IO address space, these are supported by special instructions and they are also supported by hardware protection mechanism. And there is a separate IO space. Apart from the physical memory, there is a separate IO space. Whereas in memory mapped IO, there are no special instructions. The general purpose instructions, they can be used to access the IO ports. And the protection is provided using the segmentation or paging. There is no hardware protection in the memory mapped IO. Then the last part, it is IO ports, they appear in the address space of the physical memory. That means they are sharing the address space of the physical memory. We'll see the diagram at that time, it will be more clear to you. So when we are designing the IO facility, then at that time some system engineers, they will prefer the separate IO space, whereas the others may use the memory mapped IO for simplicity, because there will be only one physical address space. Let us see the separate IO address space first. So the 80386 microprocessor, it provides the separate address space which is distinct from the address space for the physical memory. So we already know that the 80386 microprocessor, it has got 32 address lines. So the physical memory is 2^32, that is 4 GB. And here the address space, it is 2^16, that is 64K and individually addressable 8-bit ports are there. That is, the number is 64K. Now the two consecutive 8-bit ports can be treated as 16-bit port, and similarly 4 consecutive ports can be treated as 32-bit port. So accordingly we'll have the address space will remain same 64K, only the number of ports will change. So here we have shown the address space, which is 64K by 8-bit. So the address for this will be 0000 to FFFF in hexadecimal. Then let us see the 8-bit, 16-bit and 32-bit ports. So as we have already seen that the address space can accommodate 64K 8-bit ports. So but if we are combining 2 ports, it will become 16-bit port. So it will be 32K 16-bit ports. And if we combine 4 8-bit ports, it will become a 32-bit port. So that will lead to 64K 32-bit, which will be each will be of 32-bit. So in this way, the 64K by 8 ports, 8-bit ports, they can be combined to form 32K 16-bit ports or 16K 32-bit ports. Here, when the address of the port crosses the boundary between 2 double words, then in that case extra bus cycles will be required. So only that is the disadvantage of having the addresses at which cross the boundary. Then there is a signal m/IO hash that is similar to m/IO bar. So this is the pin on 80386DX microprocessor, which will indicate when a bus cycle to address the address space. Okay, so should be say low, then it will indicate that the address space is to be taken. So when separate IO address space is used, it is the responsibility of the hardware designer to make the use of signal to select the IO ports rather than memory. So this signal m/IO hash, it will separate the memory and IO. So if you the designer uses this for the selecting the IO ports, then he can use the separate IO space. Then let us go further. The address specification by a program. See, when we want to address the port, then there are 2 ways. First is with an immediate byte, the program can specify 256 8-bit ports. So there will be now this, since this immediate byte constant, so it will maximum value will be say, if it is in hexadecimal, it will be FF. So that is nothing but equivalent to 256, 255 in decimal. So we'll have 256 8-bit ports, and if we take 16-bit ports, it will be 128 ports. Now here the ports will be numbered say 0 to 4. That means only even address will be there for the ports, because say this 0 and 1 will be occupied by the first port. So each port will have 2 addresses. That's why the address will be in this case only even number. Then if you combine the 4 ports, it will lead to 32-bit ports, the number will be here in this case 64, and the address will be now multiple of 4, 0, 4, 8, like that. So the last address will be 252. So it will be having the address 252, 253, 254 and 255. That is the last address. So in this way, the immediate byte constant can specify a 256 8-bit ports, 128 16-bit ports and 16 32-bit ports. Then if you are using the DX register, then we can specify say 64K 8-bit ports. So they will be numbered through say from 0 to 65535. This is in decimal. So it represents FFFF in the decimal. So similarly, it will represent 32K 16-bit ports. So again here the address will be even address, and then 64K 32-bit ports, and the address will be again multiple of 4. So in this way, the address will be specified by the program. Then let us go to the memory mapped IO. So the IO devices may be placed in the address space for physical memory. So that we call it as the memory mapped IO. So the devices, if they are responding like memory components, they can be used with the memory mapped IO. So those devices we can use the memory mapped IO. So here when we are using the memory mapped IO, at that time we have a additional programming flexibility. The same instructions which reference to memory can be used for accessing the IO port located in the memory space, because the address for that will be the same as the memory, and so we can treat the IO as memory, and the same instructions can be used for programming. Say for example here, the move instruction that can be used to transfer data from any register and a port. So we have number of move instructions already that is done in 8086 also, and then the other instructions, that is the for Boolean operations and or and test, they may be used to manipulate the bits. So they can be used to manipulate the bits in the status registers of the peripheral device. Then memory mapped IO can use the full instruction set and the full complement of addressing modes to address the IO port. So that is the main advantage of memory mapped IO. Whereas in case of separate IO, we'll have to use the specialized instructions for the input output. So this is the diagram which is showing the physical memory, and here the ROM is shown, and then we are showing the input output ports. So these are the input output ports which are shown, and then we have the RAM or read write memory, and here just we have shown from 0 to n. So actually physical memory will be in the form of bank. So the ports can be part of any one of the banks. Then let us go to the IO instructions which are used in the separate IO. So the IO instructions of 80386 DX microprocessor will provide access to the processor's IO ports for the transfer of data. So there are say two kinds of IO instructions: those which transfer a single atom, that is byte, word, or double word. So byte is 8-bit, word is 16-bit, and double word is 32-bit from or to or from a register. So that is one kind. And the second kind here, which transfers the string of atoms, that is string of bytes or words or double words. So when we are doing using the string instructions, then these instructions are called as the string IO instructions or block IO instructions, because they are transferring a block or string of data. And let us see the instructions. First is the register IO instruction, that is in. So this instruction, in and out, there are two instructions. First we will see the in instruction. So that will move the data between IO ports and the registers. So here for 8-bit AL register will be used, for 16-bit AX register will be used, and for 32-bit EX register will be used. So in and out instructions will address the IO ports either directly with the address of one of the 256-bit 256 ports. So directly immediate addressing, or indirectly we can put the address in the DX register. That is already we have discussed that. So in, that is will transfer a byte or a word or a double word from an input port to AL, AX or EAX register. So here we have taken example. So if you give the instruction in AL, 82H, so this instruction will input byte from port 82H into AL. So 82H is the port address. So from this port, the 8-bit number or 8-bit data will be input and loaded into the AL register. Then the second case, in AX 82H. So in this case, we'll input word, that means 16-bit data from port 82H into AX register, which is 16-bit. Then if we are specifying the address in the DX register, so in AL DX, so here the address is specified in the 16-bit DX register. So we can have any address from 0 to 65536 35. So here we can input byte from port whose address is in the DX register, and that will be loaded into the AL register, which is 8-bit. Then the next instruction, that is the out instruction. So out is nothing but output from port, so that will transfer a byte, word or a double word from 8-bit register AL or 16-bit register AX or 32-bit register EAX to the output port. So if you want to use to transfer 8-bit data, will make use of the AL register. If you want to transfer 16-bit data, will make use of the AX register, and for 32-bit will make use of the EAX register. Now let us take the examples for this. Say out 32H, AL. Now this instruction, it will output the 8-bit data from AL to this port address 82H. Then the next instruction, out 82H, AX. So here it will take 16-bit data or word from AX register and output it to the port 82 H. Then the last out dx comma al. So here will output 8-bit data from al to port whose address is given in dx register. So by default dx is used for storing the address. So we'll have to specify the address of the port in the dx register, and then we can make use of al, ax or eax for outputting byte, word or double word. Then the next is the block IO instruction. So here we have two instructions, INS and OUTS. So they are used for moving blocks of data between IO port and the memory. So the address for this will be specified by the DX register. So if it is 8-bit port, will be having the address 0 to 65535. If it is 16-bit, will have the even address, and for 32-bit will have the address which are multiple of 4. So since these block instructions, they are used to transfer block of data or string of data, we'll have to make use of the SI or DI register to address the memory where the data may be stored or from where the data will be taken. So here in the string operations, we'll make use of the D direction flag. So either it will be incremented or decremented depending on the direction flag. So the register SI and DI are incremented or decremented as per the direction flag. And the in INS and OUTS, these instructions, if we are making use of the repeat prefix, then they can perform block input or output operation. The repeat prefix REP, it will modify the INS and OUTS instructions to transfer block of data between input output port and memory. So they are used for the string operations. Then let us see the INS instruction first, that is input string from port. So here either we can transfer byte, word or double word. So accordingly we'll make use of the instructions INSB for the byte, INSW for the word, and INSD for the double word. So if you take example INSB, so this instruction, it will input byte from port DX, so whose address is in DX, into here we are specifying extra segment and DI. Then INSD, this will input double word from port DX into ES:DI. So this will specify the memory location for the data to be transferred. So in this way, if we are again combining the REP prefix, then it will make repeated read cycles to the port, and it will put the data into the consecutive memory locations which are specified by ES:DI. Then let us go to the OUTS, that is output string from port. So this will transfer a byte, word or a double word string element from memory to an output port. So it is just the opposite or opposite of ints. So again, here out ESB, that is for the string byte, out ESW is for the string word, and out ESD is for the double word. So, and again, if we are combining with the REP prefix, then it will make use of the consecutive memory locations and write the data to an output port. So we take the first instruction, out SB. So this will output byte from this location DS colon SI. Here we have taken DS and SI, these two registers. So this is the data segment and this is the source index. So these two registers, they will be used for calculating the address, actual address of the memory location to port which is specified by DX. Then out ESW, it will transfer 16-bit data from this memory location to port in DX. That is the port specified by the address in DX. And out ESD, so that will output a double word or 32-bit data from this memory location to port in DX. Then the last part is the protection and IO. So the IO architecture has two protection mechanisms. The first is the IOPL field in the E flags register controls the access to the IO instruction. So this part is part of the E flags. So that IOPL field will control the access of IO instruction. And the second part is the IO permission bit map, which is a map of the TSS segment that controls the individual ports in the IO address space. Now this part, IO permission bit map, this will be covered in the next video. So these protection mechanisms are available only when we are using the separate IO address space, whereas in case of memory mapped IO, only the segmentation and paging will provide the protection. There is no protection in hardware. So this protection will be present in the hardware form. So with this, we come to the end of this video. If you have any questions, you can contact me on Facebook, Twitter, Gmail or Instagram. Then if you like the video, press the like button, share with your friends and subscribe to our channel Engineering and Technology for You. And don't forget to press the bell icon so that you get notifications for future videos on this subject. Then thanks for watching.